Welcome to the course of Network Protocols. I'm your instructor Zeeshan Bangash, and today we will be discussing the third part of Interior Gateway Protocols. This is lecture number 21. So let's move to the outlines of our today's discussion. So, uh, in today's discussion, we will be discussing another interior gateway protocol, that is the open shortest path first. It is the mostly used protocol in the routing, particularly in the hierarchical routing. And then we will be discussing the three phases in routing databases. We will also be talking about border gateway protocol, which is an inter autonomous system routing protocol, and we will discuss a general overview of the architecture of a router, particularly the different parts of the router, and then we will talk about the IP version 6, and at the end we will summarize our detailed discussion we did in the three phases about the interior gateway protocols. So let's move to the first part of our discussion. That's about the OSPF protocol. Now it's the OSPF protocol is available publicly, and it's mostly this protocol is used for hierarchical routing, and we will be discussing in the upcoming slides that what are the advantages of this protocol has over the previously discussed RIP protocol, which is also an inter autonomous system routing protocol. So there were some shortcomings we discussed in the previous session in the routing internet protocol. So this OSPF protocol is introduced. It's openly and publicly available, and its use link state algorithm. In case of RIP, the distance vector routing algorithm was used. However, for OSPF, another category of algorithm, which is a link state algorithm technique, is used in its design. Now, the link state packets dissemination occurs, and at every node in the topology that stores the every node in the complete topology stores the map about the network that's going to be shared with the neighbor ones, and it uses basically the Dijkstra algorithm. In the upcoming lectures, we will also be discussing this Dijkstra algorithm and its operation. So the roots is computed using this algorithm. Now, OSPF uh, carries one entry per neighbor root. So that entry about the neighbor is shared. Now, how it's shared? The entire autonomous system is flooded with this advertisement about the neighbor information. Now, about some of the aspects, some of the features of OSPF that provides an edge over the routing internet protocols are discussed in this slide, and one of the feature is basically this security, and the main reason is basically this TCP connection, not the UDP type of connection that is used in the design of this OSPF, which works on the three-way handshake, and it basically helps to prevent the intruder to hijack the session, and the whole session is authenticated. So this is one of the most important feature in this type of protocol to implement the security services. Now, the another important feature that was very limited in routing internet protocol, and that was limited to only one path, is basically the multiple cost paths that are allowed. So this is another feature. Now what does that means? That for each link there is multiple cost metrics, and based on the condition and the scenario, the path will be selected, because each path contains multiple costs, and that cost may be set from low for best effort and high for a real time environment. So this is another edge over the RIP to this OSPF. Another aspect is basically that it supports the multicasting and the unicasting mechanisms, and MOSPF, which is a multicast OSPF protocol, have been in the market, and that is uses the same topological infrastructure as was used by the OSPF previously, traditionally OSPF. So it supports unicast and multicast operations. And the last thing is that it's used for high and larger domains, because the main purpose of designing this protocol is to perform the routing at a larger level, and particularly at a hierarchical level that's divided into different layers. So hierarchical OSPF that can be used at the core network level or the core WAN level. So that's another edge that's extends the domain of this type of protocol. Now about hierarchical OSPF protocol. Now you can just look into this diagram, that this whole network is comprised of different routers, and that has been shown. However, when we just examine this whole connected networks, we can categorize it into level 1, or we can call it area 1, and then there's another area, we call it an area 2, or we can call it a different autonomous system, and there is another area which we call it area 3. So that complete maybe a one autonomous system. We can say that this complete autonomous system is divided into 3 sub areas, and each area have a area border router. For example, this is the area border router for area 1, and similarly this is area border router for area 2, and similarly this is the third area border router. And through these area border router, which comprise of the first level or a level, they are connected to the backbone routers. So here this is the backbone router that is connecting area 1 with the area 2. Similarly, this is the backbone router which is connecting area 2 with the area 3, and then the complete backbone routers is connected with a boundary router. So this so in the current diagram we can just that there are 3 levels. There is a top level, which is the border router level, boundary router level, and then there is a second level, we call it the backbone router level, and then there is a third level, which is basically the area border router. And under this area border router, different areas routers are interconnected, so they just report to this border. So through this area border router, inter autonomous system or inter area communication took place. And if we can just consider that this is a complete one autonomous system, so this boundary router is connected to the boundary router of another autonomous system. So the inter autonomous system communication took place through this boundary router. So this is a complete hierarchy through which can be used for large networks, for a mega networks. So hierarchical OSPF protocol is used for such a scenario. Now we can just discuss it in diagrammatically that the whole hierarchical OSPF is divided into 2 levels, and one is the local area and another is the backbone area. So the LS packet or LS packet dissemination and the advertisement we discussed in the previous slides, that is only flooded in one area. So this is the specific information that the LS packet dissemination took place only in a particular area, and each node has a detailed area topology, and they only know the direction to nets in the other areas. That's they know the shortest path information to the other areas. Similarly, there is another level of hierarchy, that's we call it area border router. So it basically summarizes the distance to the networks in its own areas, and it advertises the information or the routing information to other area border routers. So these are the two hierarchical levels. Now about the backbone router. The backbone router basically runs this OSPF algorithm, and this OSPF algorithm is limited, its operation is limited only to the backbone routers. And these backbone routers basically connect different areas. So the boundary router we already discussed in the diagram, that it's basically used for connecting other autonomous systems. So these boundary router are used for inter-autonomous system communication. Now about the phases of routing. So it's been divided into three different phases, and the first phase is basically the hello phase, and for here and I am here packet is disseminated uh, with each neighboring router in order to develop a relation. So this is basically the first phase, we call it the hello phase, and then this hello phase is followed by a DB database exchange phase, in which the router tries to tell its neighbor about the information this router has. It's about the detail of the routes or the topology or the topological information this router has with it. It shares this information with the neighboring, and then that's followed by the third phase, which is the flooding phase, in which whatever new information received by this router, and then after a specific time this information is shared, it's flooded amongst its neighbor, and new information which it receives on the partial map from the other, that's basically shared with the neighbor one, and that sharing took place at a specific interval. Now the whole process ceases after the database is being synchronized. So after the synchronization mechanism, this process, these three phases will not continue. However, the after the initiation of the database synchronization process, the three phases, that is hello phase, then followed by a database exchange, and then followed by the flooding phase occurs. Now about the inter-autonomous system, we already talked about this part in our previous discussion about the interior gateway protocols. This is an example of an interior inter-autonomous system, in which this is basically the router that is connecting one autonomous system, which is autonomous system C, with the autonomous system A, and that is connected with this router, which is the border router, which is basically the communicating router between inter-autonomous systems. So how the communication take place is just a review, that this router basically communicate with another routing protocol, and you can just look into it diagrammatically, that how the inter-autonomous system routing took place, and the information between the inter-autonomous system routing is shared. So this is basically the border routers we discussed in the previous slides, that how these border routers, which are connecting different autonomous systems, are connected and communicate information with each other. Now, another type of protocol that is used for this inter-autonomous system routing, that is the protocol which is used for inter-autonomous system communication, that's used for the border routers communication, is the BGP, which is the border gateway protocol. So this border gateway protocol is the de facto standard, and the current version that's available in the market and that's used by different router at the border gateway is the version 4. We call it BGP 4. Now, it works on the technique of path vector protocol, and it's very much similar to the distance vector protocol we discussed in the RIP, routing internet protocol. It follows the same technique for during its implementation. Each the border gateway broadcast the information which it has to its peer border gateway to which it is connected, and the entire path is shared to the destination. So all the information the autonomous system border gateway protocol border gateway router have, it shared it with the neighboring border gateway router. Now, for example, if the gateway X or the border router X wants to send its path to the destination Z, so the path can be from X to Z, that is the X, Y1, Y2, Y3 up to Y that is shared with its neighbor border gateway router. Now, suppose that the gateway X wants to send its paths to a peer gateway, that is W, is the neighboring gateway with which this W with which this gateway X is connected, and X has the information of connecting it to another gateway which is Z, and there is no direct connection or information of the gateway W with the gateway Z. So how this inter-autonomous system routing can be represented? So W may or may not select path offered by X. Yes, that's exactly. So the cost on the links may be so why this W may not want select path offered by X. So it's up to the autonomous system that it cannot accepts whatever the information it receives from the neighboring gateway routers, that it may result in the loops, and the main purpose is to avoid loop, and it may be the autonomous system policy by the administrator that it will not accept information or the path information from the neighboring autonomous system, and that's again depends upon the cost which it offers during the sharing results that it will not accept the information from the neighboring autonomous system. So if the W, however, selects the path advertised by X, then we can just look into it that the W which is accepting the path and the X has already the path of the set, so now the W has the path for the gateway router Z as well. Now note that X now can control information incoming traffic control its route advertisement to the peer. For example, if you don't want to route traffic to Z, so we need not to advertise any routes to Z. So this is basically the controlling that can be managed for limiting the traffic coming from or forwarding to a particular autonomous system. Now, the important feature of BGP is that for exchange of information, like the OSPF, it uses a connection-oriented protocol, which is a TCP sessions, which works on a three-way handshake, and the BGP message comprised of an open TCP connection to peer and authentication. So the inter-autonomous system routing, particularly the BGP protocol, have an open message. We discussed it, that it basically opens the TCP connection, and then there is updation about the new paths that have been added to the routing table, and for that an update message is flooded among the neighbor autonomous system. And then there is another uh, uh, message that is flooded and circulated among the autonomous systems in case there is if there is no updates in the routes, and that's a keep alive message, so that in order to update about the neighbor gateway routers that the connection is live and the connection is not broken, and upon receive of this update keep alive message, an acknowledgement open message is also requested. And then there is another BGP message, which is the notification message. So the notification message is used to report errors in the previous message, and it's also known as the close connection message. Now, what is the difference between intra and internet autonomous system routing? So the first difference is basically on the base of the policy, that in case of inter autonomous system, the administrator of the networks, they uh, in order to design that networks, this administrator wants control over the traffic that is routed, that whoever routes through his network, so this traffic needs to be administered. So in case of inter autonomous system, the first difference is based on the policy matters, that's an administrative oriented policy. And in case of, however, an intra autonomous system, there's only one single administrator of that complete autonomous system, and for that the protocol performs its operation and no policy decision is needed, and the communication takes place based on the type of the algorithm or the intra autonomous system algorithm that is used. The second difference between inter and intra autonomous system is on the basis of the scalability issue, that in case of hierarchical routing, the table size is reduced because the table portions are stored of a particular level at different gateway routers. So it basically the congestion is reduced because the updation of the routing table is reduced to a particular area. And the third characteristics that make the difference in case of between the intra and inter autonomous system is basically the performance metrics. In case of intra autonomous system, the main concern is to focus on the performance. So because it's connecting the border gateways or the border routers with other autonomous system, so performance is of key importance. However, in case of inter-autonomous system, the policy characteristics, that is the control over the traffic that is to be moved, that dominates over the performance issues. So these are some of the differences between intra and inter autonomous system routing design and consideration. So let's talk about some basic architecture of a router. So the router have basically two key features: that it runs an algorithm, that is the routing algorithm, and different protocols we already discussed in the session 1, in the part 1, part 2, and in the current session, that is RIP, OSPF, and BGP, which are working on different techniques for calculating the route. So the first function is basically the routing algorithm that is to be run, and the second thing is this basically the switching of datagrams from incoming to outgoing links. So an architecture of a complete router is shown, in which there are some input ports. We call it the input interfaces, and then there are output interfaces. Depends upon the type of the router. In case of modular router, you can add input and output interfaces, and then there is a switching fabric that basically switch the incoming packet to different output interfaces, and then there is another routing processor that's basically used in order to switch that fabric that is connected with the switching fabric. So this is basically the general architecture of any router, which comprise of four different parts: the input ports or interfaces, the output interfaces, the routing processor, and the switching fabric. Now about the input port function. So the port function is again divided into three parts. The first part is the line terminal, which is basically the physical layer that's used for the bit level bits receiving, or it is a bit level receptor. And then the bits that are received, that's forwarded to the second part of that input port, that's basically the data link layer, and that's basically processed by the data link processor, and it's used for decapsulation of as per the header information, and then that is forwarded to the third part of the input interface, which is the which is known as the decentralized switching, and it's used for looking up or forwarding, and a queue is generated based on the priority of the data that is, or the input that have been received, and then the information or the queue is forwarded to the switching fabric. Now basically in case of decentralization switching, based on the datagram destination, our lookup output port is routed to a particularly the input port memory. Now the goal is basically to complete the input port processing well in time and in speed. And in terms of queuing, though, so if the datagram arrives faster than the forwarding rate into the switching fabric, so this decentralized switching manages this operation. Now about the input port queuing, it's basically a fabric slower than the input port combined, and the queuing may occur at the input queues, and queue datagram at the front of the queue prevents other in queue from moving forward, and we can call it HOL blocking, head of line blocking. It's used for pausing the communication, and this queuing delay and loss occurs due to the input buffer flow, and as a result, the whole throughput of the router is managed because of this HOL blocking. This diagram again explains the how the queuing performs. Just look at the output port at time t, that it is here it is only reading the red packet that the switch fabric is forwarding to the output port, and the green packet here in this diagram is basically facing an HOL block, so it is blocking other in the queue from moving forward. So green packet here is facing HOL blocking. Now there are three different types of switching fabric. One is the memory switching fabric, bus switching fabric, and the crossbar switching fabric. Now the switching wire memory, it was manufactured in the first generation of routers, and the packets are copied by the system's CPU, and then the speed is limited by the bandwidth, the memory bandwidth. So for a unit diagram, two bus crossings were designed for it, and you can just look into the diagram that there are two bus crossings per datagram in this first generation of routers. And however, in case of modern routers like Cisco Catalyst 8500, the input port processor performs the lookup and it copies it into the memory. So an advanced feature introduced into the modern routers. Now again, the second is the switching wire buses. So you can just look into the diagram that datagrams from input to the port memory output is managed through the shared bus, and this bus is shared. And normally the switching speed is as again has a limitation that is related to the bandwidth. So it has a bus contention mechanism because of the bandwidth constraint of the bus. And there is 1 Gbps bus in the Cisco 1900 switches, and the speed is sufficient for the access of an enterprise router, and it's not used for regional or backbone router. Now the another type of switching is switching via interconnection network, and it's overcome bus bandwidth limitation. And example is like the Banyan's network and other internet connections that were initially developed to connect the processors in a multiprocessor, and it has advanced features like fragmenting datagrams into a fixed length cells and switch cells through that fabric. And Cisco 12,000 switch an example that switches the Gbps through that interconnection network. Now the output ports, that output port again is divided, that is connected with the switching fabric into three parts. There's a queuing buffer manager for outputting on the output interface, and then again there is a reversal process of data link processing that was the same part as in case of the input ports. It decapsulates. In case of the input ports, it capsulates. However, in here it decapsulates, and then there's a line termination that converts that information or the data into a series of bits for onward transmission it to the network. Now the buffering required whenever the datagrams arrive from the fabric faster than the transmission rate. So because there is change in the speed of the receiving and the sending, so the buffering occurs then. Now we need scheduling discipline. Let's choose among queue datagrams for transmission because there are multiple queues created. Now the output port queuing is shown in which the output in this first part of the diagram, that output port connection at time t is shown, and one packet is outputted at a time to the different outputting queues. You can just check this in the diagram. Now the buffering when arrived rate via switch exceeds output line speed, so the queuing and delay and the loss due to the output port buffer overflows the whole scenario. So as far as the IP version 6 is concerned, previously the IP version 4, that was a 32-bit address space that completely allocated by 2008, and it was completely filled. So additional motivation was that the header formats help speed processing and forwarding, and second thing is that the
header changes to facilitate the quality of services, and new any cast address route to best services replicated servers introduced. In case of IP version 6 datagram format, the fixed length of 40 bytes header was used, is used in fact. And here in case of IP version 4, version 6, no fragmentation is allowed. So in the complete session of 3 sessions of interior gateway protocol, we discussed the concept of autonomous system, and which is used as a hierarchical routing paradigm that's supported by the internet. So we discussed that. Then we discussed different interior gateway protocols like RIP, OSPF, and BGP. That's the routing internet protocol, open shortest path first, and the border gateway protocol, in order to grasp the essence of protocol design and what needed to be addressed in addition to the algorithm like distance vector and link state algorithms. And then we discussed in the last slide about the IP version 6, and discuss some challenges, that how it is difficult to make changes in the network layer, thinking replacing or changing the foundation of a complete house. So this is the reference which I followed, and you can consult it for further details. And you can also email or send your queries through WhatsApp number I have already shared. uh, Thank you very much for patiently listening. Take care. Allah Hafiz.